the topic today is on these ideas of dimensional reduction, agents, and models. So let me begin with just a quick introduction to my group. So we are a group at NTU. So it's a quantum and complexity science initiative. So our focus is in interfacing the ideas of quantum information and quantum computing with ideas from complexity, data science, and machine learning. So it's quite a nice interdisciplinary group. We have about 20 people. But what I want to talk about today focuses on a particular area of this. And it's a notion of playing games and the notion of dimensional reduction. So I want to motivate this with a game. So this is a game of blackjack. It's commonly played in casinos. Many of you will be probably familiar with it. For those who are not, the basic idea is that we are playing against a house, a casino, and the goal is to reach 21, or as close to 21 as possible by drawing cards, but never hitting 21. But the key take-home message for this is that this is a game in which if we didn't remember what cards have been played before, then the casino on average always wins against us. So if we keep playing, eventually we lose all our money. But if we could know some information about what has occurred in the past, so if we could count the cards, then we have a better prediction about what cards will come up in the future. And when we do that, it turns out that we can gain an edge over the house. And on average, we can actually win. It's one of the very few games in which you can on average win against the house. And this is why there's a big movie, The Code 21, in which highly fictionalized, but there was a group of MIT students at some stage that cleaned up a couple of casinos by sort of playing blackjack and got kicked out of these casinos. Rest of the movie is fiction, but that's probably still enjoyable to watch. But the take-home message here is that if we wanted to succeed in complex environments, then we need to take into account what has happened before. And in the case of the game of blackjack, what the observations we make is basically what cards have been played. The actions we can take is choose how much money we decide to put down. And if we knew something about the cards, in particular in this game, if we could track the number of high cards, then the more high cards there is, the more likely it's favorable to us. So we put down a lot of money when there is a lot of, when we're more likely to get sort of high cards, and otherwise we do not. So this is the basic idea. Now, the thing, of course, is that if we didn't understand on the statement, then we may not know that it's a high cards that are valuable. So we might want to track everything. And indeed, if we track everything, we can play a bit better than even in just tracking the high cards, but it's a lot more memory, a lot more effort, and it's not usually humanly possible. So what makes blackjack possible is that the key features that allow us to win is relatively simple. It's just tracking the number of high cards. And to know that, we have to have some understanding of the game. So the idea with sort of navigating complex environments is that, one is that we do need information about the past, and two is that if we could understand the environment a bit better, then we know which features we should keep and which features we can discard without too much adverse effects. And so with this in mind, this sort of game playing, of course, it's not just blackjack, and it's, this sort of agent behavior is rife in sort of everything from large language models, where you're trying to sort of track and predict the next token, to say self-driving cars. It's all really about tracking which elements of the past that is of potential relevance in the future. And in this case, often the key thing here is which aspects of the past is of the most relevance to the future. And as our environments gets more and more complex, so even in blackjack, casinos are adding more and more deck of cards, so we have to track more and more cards. But in general, as we're tackling these more real-world problems, like the human language, then we need to track an immense amount of information. And of course, if we could understand that system a bit better, then we may be able to isolate which pieces of data that is most relevant for what we want to do. And so this is kind of the motivation behind some of these notions of what's called model reduction. We start off with something, a model, that tracks everything about the past to make potential predictions about the future. And this tends to happen if we have no understanding of what's going on. We just feed everything into our giant transformer, hope for the best, and if we have enough memory, then yes, we can do pretty well, but at does take a lot of resources. But if we are getting a better understanding of things, then we are able to discard information that are perceived as less relevant, and maybe we can do so without really affecting the performance of our models or whatever task that we're trying to solve. And this is really what's behind sort of the running philosophy of physics for a very long time, known as Occam's razor. The idea is the understanding comes when we can isolate the pieces of parts that's most relevant for future predictions. And indeed, it's this kind of notion that was first studied and formalized by a guy called Jim Crutchfield, now director of the Complexity Science System at UC Davis. And he sort of gave a formal definition to try to understand sort of what information we need to be able to sort of replicate certain behaviors, execute certain strategies. And so he gave this formal definition of a strategy. This is the basic idea of this is that strategy is just a family of stochastic processes, so it's a family of probability distributions of what we wish to output in the future, but that family is kind of parameterized by a sequence of possible future inputs. So with every possible future input, we have a potentially different designated future behavior. This is the most general way of defining what's known as input-output process, and then the goal of basically executing a complex strategy or building a general model is to track enough information about what happened in the past, so that's just the ordered pair of past inputs and past outputs, so that we are able to replicate the right conditional future behavior regardless of what future input we are given. And so once we can specify, so if we specify that, then we have a full specification of strategy. Now, in general, we never specify strategies this way because that's like that's an infinite family of stochastic processes, but this is a mathematically formal definition. And in this way, it encompasses these ideas of stochastic modeling as well. Stochastic modeling, or just a prediction of time series data, is just a special case where all the inputs are just a single symbol, so just zero. The idea is we can't actually affect the future, we just want to model the future. So that's a subcase of this general area of sort of building and executing these complex input-output processes. And what Crutchfield came along was he defined this notion of the minimal models that could do so. So he called these minimal causal models. And the basic idea with these models is that the dynamics of any of these complex input-output processes can be thought about as taking the relevant past information, storing it into sort of some physical system with some number of states. These are the internal state of the system. And such that the dynamics or the behavior that we want can be completely described by a single transition probability matrix or tensor. Basically, the probability is sorry about that, it should be the one up top, ty given x, jk. It's just the probability that we start from some state sj, and on input x, output y, and transition to probability sk. So it's this 4-parameter tensor object, and once we use that, once we sort of specify that, then the entire input-out behavior of this machine is specified. And what Crutchfield was interested in was the simplest machines, or the machines that used the least amount of memory to be able to execute a given input-output strategy. So we imagine we have some sort of behavior, maybe it's winning the game of blackjack. We know what is the best possible way to win, the one that gives us most returns. That's a particular input-output process. And then once we feed that in, then we can look for, okay, what is the simplest machine that can replicate that sort of behavior. And when we sort of, once we define such a machine, Crutchfield showed that in principle such a machine always existed, and of course, finding them in real-world situations can be highly challenging, but in principle they always exist, so we can define these machines. The simplest machines, the states here are referred to as a causal states, and referring to the fact that they're kind of the causes for future behavior. If you know these states, then we know how the machine will behave in the future. And he gave these two different measures for the memory cost. The top one is known as the statistical complexity, and it's just the Shannon entropy of the symbols as they propagate through. So you can think about that as a minimal number of bits that we have to communicate from past to future to be able to replicate this behavior in a causal manner. And this is because it is a tropic quantity. This is a kind of a IID measure. So it measures the memory cost per instance of this process if we're trying to simulate or replicate many copies of this process at the same time. There is also the topological complexity, which is just log base 2 of the number of different possible states or the dimensions of that memory, and that corresponds to a single shot measure. That's basically how many bits of information I need to be able to replicate this process if I just want to replicate a single copy. Yeah?
So neither of those take into account correlations between, it's almost like each thing that arrives is kind of random and independent of the one before. I'd have thought that if you know there's some kind of ordered sequence or there's some kind of memory, there's correlations between them, that there's an order that they're similar.
Right, so you mean like correlations between different times?
Yeah.
So absolutely, so there will be potentially correlations between different times, but this is kind of like a cutoff between the past and the future. So what we're looking at is just, you can imagine that Alice has this information and she's trying to communicate that to Bob, who has this piece of information. So she's just communicating the state at the current time. And so in this sense, if you have many copies of many instances, they're statistically uncorrelated. So it just boils, the IID just boils down to the Shannon entropy of that distribution. But you're right, if we are trying to communicate the state of the system over many time steps, then we can potentially compress it further, because the state of the system at this time will be correlated with the state of the system at this time. So these are these minimal models. And well, the first thing that Crutchfield sort of applied this to was to use them as a model of a certain sort of complex phenomena. So this is the discrete dynamical system that many of you may have seen as was often called as a transition to chaos. Basically, this is a discrete model that relates x at time t+1 to xt. So this is just modeling a stochastic process. You can think about this as input-output behavior where there is only a single possible input. You can, of course, view a model of this process using sort of Crutchfield architecture. And so what Crutchfield did was he took various possible discretizations, so he would bend the xt into various discrete time steps, and in general, this behavior emerges regardless of how we choose to bend the system. The basic idea with this dynamical system is if this R value is sufficiently small, then the long-term stationary behavior is that it just converges to a steady state. And so it has a particular equilibrium state. And when that's the case, then the amount of memory we need to communicate is basically zero, because it's going to be in that state the whole time. So we don't need to know anything about the past to know that it's still going to be in that state. But as we sort of continue and raise the R value, then you get this period doubling behavior. So the stationary behavior now oscillates between two different possible states. So if we want to predict how it will happen, what will happen in the future, we need to track which part of that period is in t, is it time even or time odd. And so we need one bit of information as we continue across. And as we keep period doubling, as the periodicity gets higher and higher, so we have to kind of track more information about what happened in the past. And that's why we can see that we have a steady increase in the amount of information we have to track to be able to replicate the right behavior, right out this transition point to chaos. And that's where, in principle, this thing jumps to infinity. Of course, in numerical simulation, it doesn't quite get there, but you get this phase transition. Afterwards, the dynamical system transitions to a chaotic behavior where it starts looking progressively more random. And once things get more and more random, the amount of information we need to replicate the behavior tends to go down, because what happens is that in the extreme case, it just becomes a random sequence, and to replicate a random sequence, we again need no memory. We can just close our eyes and just keep throwing coins. And so you get this kind of this behavior that isolates this point where the system is, in a sense, the most complex. And so the first uses of these tools was to quantify complexity. And if you're interested in that, Crutchfield has a nice nature physics review there about between order and chaos, where he sort of looked at how these tools can be used to understand complex systems. And indeed, it's in this place, in this transition point, where we expect the most interesting stuff to happen, because that's where we get universal computation. This is where things are very difficult to predict. And indeed, when we are trying to model very complex systems, nowadays in machine learning, sort of when we're using, say, transformer models, what we find is that the amount of memory that we need is really growing exponentially as we try to tackle more and more complex tasks. So this is a nice graph of the resource cost of various different models. And since the birth of transformers, we've seen the resource grow at a rate of over 200 times every 2 years. So that's kind of insane because, Moore's law is only like 2 times. We don't even really have Moore's law anymore. And if you take a more physical interest, then it's actually Kumi's law, which is the amount of energy needed for computation. That currently doubles about every 2.6 years. So we're really looking at 2 orders of magnitude more growth in cost than efficiency. And this is why, under current expectations, the energy consumption of machine learning and AI models will exceed global energy production by, the mid-2040s. Obviously, that's extrapolating this line. That's never going to happen. Conservation of energy and all that. So we're expecting a bottleneck. And this is, of course, why some Altmans, they say we need to build some nuclear fusion plants to power the next generation AI. So we're kind of at the stage where we see that as we're modeling these more complex behaviors, which have book-length correlations, then it's the amount of parameters we have to track is growing immeasurably. And indeed, most of the energy constraints turns out isn't in training, it's in the inference. Because training, you train once, inference, we infer forever. Every time a user uses it, we have to run the inference. And so this cost is expected to, inference cost scales with basically how much memory that we're tracking. Now, so, and also sort of, and this motivates this notion, well, do we need to really track things exactly? How about we track things approximately? What features do we really need to keep? And so in the extreme case, we know that when we're tracking very complex systems, the memory shoots up when we want our model to perform as well as possible. But if we allow some distortion, if we allow some slight loss of performance, then maybe we can use drastically less memory. And so classically, there's been a lot of work towards various different model reduction methods, such as classical quantization, in which we trade off performance with memory cost. And so this is not to be mixed up with quantum mechanics at all. This has nothing to do with quantum mechanics. It's just we take a classical model, which if we're looking at, say, transformers, or we're looking at RNNs, recurrent neural networks, they have a bunch of continuous parameters, and we try to discretize them. Instead of, say, a 32-bit float, we use a 16-bit float, maybe an 8-bit float, or extreme quantization, we use a single bit. That usually does badly. But we try to sort of, we experiment. We see how far we can get. And that involves this basically traces along this curve as we trade off between memory and performance, or memory and distortion. And so that's kind of where we're at. Now, what we're interested in here is, being a quantum group, is can quantum do better? What happens when we introduce quantum mechanics? And what can quantum mechanics tell us? And can quantum machines, so quantum agents, sort of that take inputs and emit outputs, fundamentally perform better than classical ones? So we take our architecture to mirror exactly the classical model. So here is what we refer to as quantum agent. You can also think about it as a quantum sequence model. Basically, it takes inputs at each time, emits output at each time as well, input xt, output yt. Instead of classical stochastic matrix or classical policy, what we have is a quantum policy. So this is some generic quantum process. And the quantum agent basically propagates along with, and the part of the agent is the stuff inside that dotted space. And this object, for those of you who are familiar with non-Markovian quantum systems, is often referred to as a quantum cone. If you've never heard of the word before, don't worry about it, we're not going to mention it again. But the basic idea is that people have used these tools to model non-Markovian open systems. And we're going to use these tools to understand, well, the other way, instead of trying to understand a non-Markovian quantum system, we're going to see how we can engineer a non-Markovian quantum system to do what we want it to do. And the idea is we have some specified input-output relation, and we want to replicate that with one of these quantum machines. And the question is, can we do better? So, to illustrate and convince everyone that there is hope in this, we're going to do a very simple example, which I refer to as quantum replicant. In reference to Blade Runner, I don't know how many people still watch Blade Runner these days, but when I was young, it was certainly popular. The basic idea was imagine that we have a machine under interrogation, and this is a very simple interrogation. To be able to win, the machine is just has to initiate this sort of very easily described behavior. Basically, each round the machine is asked one of two possible questions. In honor from Big New Zealand, one of those questions is about sheep. So that's Z equals 0, do you like sheep? Z equals 1, are you human? And to win, the machine just has to give the same answer when it's asked the same question consecutively. Otherwise, the machine is required to answer randomly. So those are the two conditions. And we want to be able to replicate this behavior with perfect statistical fidelity. Now, the question is, how do we do that? So first of all, if we think about this question classically, there are really two bits of information that is relevant. The first bit is which question was asked in the last time step, and the second is what was our answer to the last question. And we need both bits of information to be able to perform this game exactly as specified. And indeed, we can build such a machine. It's not very complicated. It's just a dimension 4 machine, a machine with a 4-dimensional memory or 4 distinct states, which so it's a 4-state finite state machine like this. And each one of these basically corresponds to a combination of which question was asked and what was the last answer. Here I've color-coded the inputs. So the green inputs are the first question and the gray inputs are the second question. So you can see if we say over here up top, that corresponds to the last question asked was, do you like sheep? And the answer that the agent gave was yes. So if he was kept asking this question, so if he was kept asking Z equals 0, the sheep question, then he would maintain consistency because there's only one green arrow there, and he would always sort of transition back to the same state. But if he was asked the other question, sort of Z equals 1, then what would happen is he would transition to one of these two states at random, corresponds to being asked, are you human? Answering either no or answering yes. And if you follow this logic works, and then we get a machine that gets the exact statistical behavior that we would like to have. And we see that it has 2 bits of data or a memory of dimension 4. And classically, there's no way to get around this. We do need all that information. The quantum mechanically, though, we can actually do a bit better here. The trick is to encode these 4 possible states into the 4 possible states here of a block sphere. So instead of using 2 classical bits, we use a single qubit, taking advantage of the fact that some of these states are mutually non-orthogonal with some of the other states. And in doing so, we have a memory saving. We have compressed 2 qubits into a single qubit. And of course, one would ask, is it still possible? Can we still generate the right behavior this way? And the answer turns out to be yes. Here is a circuit for doing that. It does look pretty complicated in circuit form, but it's actually not that mysterious. If we follow it through, what we have is the input, it comes across here. The input doesn't control Hadamard, and this here is just a measurement. So what the input here is controlling is whether we decide to measure in a computational basis, that's if this was 0 and the Hadamard was there, or we measure in the complementary x basis if the Hadamard was there. And so basically the input tells us whether we're measuring the x or the z basis, and we simply output the result of that x or z basis measurement. And if we propagate through, this is our quantum policy. It turns out the state of the memory is updated to exactly the right state so that we can replicate the right behavior over time. And if we think about it a bit harder, well, there's no mystery there. This is really just a Stern-Gerlach experiment in disguise. We're just taking a spin, and we're choosing to measure in x basis. If we're asked one of the questions in z basis, when we ask the other questions. And as we know with the galactic experiment, if we measure the spin on the same basis, we always get the same outcome. Otherwise, we get something random. And at this stage, you might say, okay, this was just reverse engineered, and I would say, yep, exactly, this was reverse engineered. But this kind of gives an illustration that there are, at least in these sort of very artificial engineered cases, there are cases where quantum has a definitive provable advantage. So how general is it, and why is it there? To be able to generalize, we need to understand what causes this. And that's where we want to dig a bit deeper. So why does this work? Why is it that the quantum agent could outperform the classical agent in this instance? So I want to do, in this case, return to this with another thought experiment. So imagine that we are interrogating one of these agents, but our goal is a bit different. Our goal is to understand whether the agent experienced one of two possible different paths. Whether the agent experienced path A, where he was asked, did they like sheep, and answered yes, or path B, where he was asked, are you human, and answered yes. Now, the task we have is, through future rounds of interrogations, could we ever determine with perfect confidence whether the agent experienced path A or path B? Now, if we think hard about this, it turns out that this is impossible. There's no way through future interrogation to know whether the agent experienced A or path B. And the reason for that is because we know that we could have implemented the agent using that quantum construction that I had before. So if I could, through a sequence of future measurements, determine whether the agent experienced path A or path B, then I could distinguish perfectly between zero state and a plus state, which obviously is a violation of the quantum uncertainty principle. So this is something that we simply cannot do. And so now, if we go back to the classical agent, though, the classical agent does the classical agent had two bits of data, and one of those bits was devoted to distinguishing which question was asked before. So the classical agent did use enough memory to be able to completely distinguish these two different paths. But we're just saying that no matter how we choose to interrogate in the future, so no matter what future the agent ever experiences, not all the information about that path is being propagated in the future. We can never, through the agent's future actions and reactions, sort of retrodict which path the agent came from. So we could never retrodict the true value of this bit. Part of the information used to store that bit of data is fundamentally being erased during this execution process. And one can formally define this. So in the paper, accompanying paper here in the PIX, we did give a more mathematically formal definition. But the basic idea is, if you ever have features like this, in which information is lost through future propagation. So if the classical agent is ever storing any binary feature in which no future interrogation method can distinguish the value of this binary feature with perfect fidelity, and this is what we mean by the agent is wasting information, there is always a way to construct a quantum agent from that classical agent that can replicate the behavior with no statistical loss, but less entropic memory, so less memory in the IID scenario. So this gives us a very general form of when this advantage occurs. We just have to isolate one piece of that data, so give us any machine learning model, as long as I find one bit in which this happens, then in principle quantum can be better. And indeed, one of the ways in which we can, one of the consequences, is that we can find scenarios in which we can take sort of a continuous parameter. In fact, I shouldn't say scenario. In any general scenario where where the optimal behavior depends on some continuous parameter. Now, classically, when that happens and we have a finite memory, we can't track that parameter lambda with perfect precision, so we approximate it with a finite number of bits, 16-bit per bit. So the first thing we note is that if we build these quantum models for stochastic processes, here's where the input is always the same, because we just try to model some stochastic data. So it turns out that what our models do is exactly generate one of these quantum samples of future, so a probable superposition of all possible future behaviors. Basically, you run the memory through, you have the sequential application of the unitaries, turns a bunch of uncorrelated qubits into this vast entangled state of all possible conditional futures. And so we do have that resource available, but the key thing here is that the memory that we need to do so can be a lot less than we would need classically. And in this case, though, we do need to do something a bit more sophisticated. Previously, we just looked at entropic memory. And in entropic memory, okay, your memory may be reduced, but the number of qubits may not need be the case. So we need to do this in a single shot. We need to look at how much, whether we can use less qubits to just model a single copy of the stochastic process. And so what we're looking at here is a bit different from before. Before we were looking at exact replication. We showed that maybe quantum has an advantage over classical. But what we're interested here is if we have a fixed memory, can the quantum do better than the classical with a fixed memory? This is more typical in machine learning modeling tasks. We have a certain amount of physical resources, and we just want to be able to model something as effectively as possible. And so in our recent work, what we were able to demonstrate was whenever there is a sufficiently high entropic gain, there's also a gain in the single shot level. So basically dq, d mu here is the minimum number of dimensions, the minimum number of memory dimensions needed by a classical model. We know that the number of qubits that's needed quantum mechanically is going to be at most that of classical, because we could just run the quantum model like the classical model, but sometimes it might be a bit reduced. But maybe it's not reduced by that much. The key thing, though, is that suppose our entropic memory is reduced by a lot, and the entropic memory, we have a systematic method for building these things. Then, as long as it's reduced by a lot, then we're guaranteed that if we build a quantum model with significantly reduced dimensions, the distortion that we have, so the loss in efficacy of the model, and the distortion we typically measure in terms of KL divergence, is going to be bounded above by a ratio of basically the dimensions of our quantum model and the dimensions of quantum model and that of the classical of the quantum sort of the IID memory of the quantum model. So what this is saying here is that here is the dimensions of our classical model. Here is the memory cost of our quantum model. If the memory cost of quantum model, the IID, is a lot lower, then we can always build a quantum model that uses fewer qubits, that whose distortion is guaranteed to be sufficient to be bounded, and so we are guaranteed that we can get this advantage in terms of in the single shot level as well. And what happens? So as an illustration of that, here is an example of a Gaussian random walk. So here is the case where we have many different parameters. So the Gaussian random walk is essentially Brownian motion. So imagine modeling Brownian motion on a ring. Now, if we had a ring structure like this, if we want to model exactly, then we basically need to track the position of that particle to infinite precision. And so the more accurately we want, the more classical bits that we need. Now, what happens here is, imagine here, take the example of, say, the Gaussian walk, so that xt, yt plus 1 is related by yt, by just some Gaussians centered around where yt originally was. So what we have here, the solid lines, is basically our quantum models with dimension 3 memory, dimension 5 memory, and dimension 7 memory. And the dotted lines are the optimal classical models with the same number of memory dimensions, so 3, 5, and 7. On the vertical axis here, what we have is a KL divergence. So that just measures the distortion, how close our models are to the true model where everything's modeled to infinite precision. For the simple case of Gaussian walk, we can work out these things analytically. In general, we can't, but in this case, it's possible to know what the true model is and work out these things analytically. And what we see is that a quantum model with just 3 dimensions here is as good as a classical model with 7 dimensions. And if we had a quantum model with 7 dimensions, then the KL divergence, the distortion, is around about 4 orders of magnitude better than their classical counterparts. So we can significantly reduce the memory cost, or if we want the same level of distortion, and if we have the same amount of memory needed, then our distortion can be drastically reduced. And indeed, we were able to illustrate this in collaboration with the experimental group in quantum optics at USTC, where we could witness this sort of behavior with up to about 1 order of magnitude advantage in experimental settings. This was done in optics, because optics you can do things very accurately, better than what we can do in IBM quantum computers, but of course it doesn't really scale. So this was basically a single qubit experiment, but it was a single qubit used, well, that could replicate behavior maybe 3 or 5 classical bits. So that's so we are able to kind of illustrate this in experimental settings. And in terms of time, briefly, I will just seems like I'm using slightly more time than I anticipated, so I'll go through this a little more quickly, is that we started off talking about energy, the energy costs. It turns out that these benefits translate to energy as well. And for those of you sort of who are unfamiliar, when we talk about agents, actually agents came from the physics community first, before computer scientists kind of took it over, where most of the researching agents are now in computer science. The first agents actually came about from the study of Maxwell's demon. That's the first time where agents came into the scientific literature. Maxwell's demon is, for those of you who are unfamiliar, they're basically a way of thinking about energy extraction. And they came from this notion that if we had a demon that could measure the environment and see whether a particle on the left side or the right side, then he would be able to couple weight on the right side and be able to kind of do work, extract energy from that environment. And so there's a notion that thermodynamics is fundamentally linked to this sort of input-output behavior. So in this sense, Maxwell's demons are closely related to that of agents. So when we compute more efficient quantum agents, maybe we can say something about energetics as well. And indeed, this is in its modern incarnation, Maxwell's demon gave rise to the notion of information batteries in quantum computing. And it's the idea that if we wanted to do any physical process, then we can look at the minimum amount of energetic cost of doing that process by thinking about it in this picture. So here's our system input, our system output, and we can characterize the amount of information, amount of energy that's needed by what's known as information battery. Basically, we have some initial sort of information reservoir. It could be pure qubits, for example, that have a lot of free energy. Then when we couple this to execute this behavior, usually what happens is that our battery tends to lose its free energy. So it gets messier, it gets more entropic. And the amount of entropy loss here can be thought of as a formal way of quantifying the energetic cost of a particular quantum process. Because afterwards we need to spend work to be able to recharge these batteries, to be able to compress them, to be able to purify them. And so using this framework, we can derive bounds on how much energy it costs for an agent, either classical or quantum, to execute the same strategy. In the interest of time, I won't go into all the details, but the framework is basically we have this agent. Every time step is receiving inputs, emitting outputs, and it's sort of converting nicely charged batteries into less charged batteries. And once we do this for many, many time steps, we can take all these batteries and we can sort of take them to the factory and recharge them. And the amount of energy needed to recharge these batteries is kind of like the per step energy cost of such agents. And it turns out that when we sort of work through all the formalities, what we end up is the energy cost is related by precisely this equation here. Now this equation here, here's energy dissipation. That's a fundamental energy that irreversible energy that the agent consumes. So this is the energy converted to heat, can never be used again. And it is related, these are just constants, temperature, so we don't worry about them, but it's related by a difference between these two quantities. The first quantity here is the amount of information the agent needs about the immediate past. The mutual information of the agent, the immediate past, his last input, his last output, and his current memory. And the second quantity here is how relevant that memory is to the present. So basically, the dissipation is precisely per time step loss of relevant information. So it's information the agent stores at time step t-1 that is not propagated into time t. That information is discarded in the environment as heat, and that causes fundamental energy dissipation. This is a relation that works for any agent, classical or quantum, so it's a universal bound for any agent executing a strategy. And what we can show, of course, is that since quantum uses less memory, it uses less energy as well. And in particular, in our example with the sheep, the classical agent required 2 bits of memory, the quantum agent required a single bit of memory. And it turns out because all the memories of the immediate past, the mutual information is exactly 2 and 1. And when you work out the sort of all the details, the energy dissipation of the classical turns out to be 1.5 kBt per time step, or the quantum is 0.5. Their difference is 1, and the quantum is 3 times actually more efficient than their classical counterparts. And so in conclusion, I guess main messages of this is first of all that when we sort of, the quantum mechanics offers enhanced dimensional reduction. So basically, when we are looking at replicating particular input-out behaviors, or particular stochastic processes, when we go to the quantum regime, we can get better performance. When we limit the amount of memory, our quantum agents can, essentially they're more expressive, so they can reach a larger set of possible behaviors. And that allows us to execute certain strategies more effectively. And this advantage synergizes with things like Grover search. So we can get this advantage beyond just quadratic advantage of Grover search. We can get the advantage from using less samples, but each sample we can also use less memory. And since it's a multiplicative advantage, that means that maybe we can see a lot of these quantum Monte Carlo methods more more recently, or more closely, with a shorter time frame than we otherwise expect. And finally, of course, these things actually do have immediate consequences in terms of fundamental energy costs of executing particular complex strategies. I'd like to take the last 3 minutes to just quickly mention a few outlooks. I'm not going to cover any of these in detail, but if you're interested, I'm happy to discuss. I focused here today on what I refer to here as QC. So these are quantum agents interacting with classical environments. The quantum agents trying to execute classical strategies or predict classical data, classical stochastic data. But just like machine learning, where we can also have CQ and QQ for agents, we do as well. We can have classical agents interacting with quantum environments, or quantum agents interacting with quantum environments. And these things are interesting in their own right, because if you look at CQ, it's really about control. It's about using classical agents to control quantum systems to make them do what we want them to do.